Bus servos are great as they can be chained with fewer wires, take out fewer GPIO outputs and give feedback on motion. They need driver modules, or do they? I've been taking a look and I'm a little surprised at what I can achieve. Let me tell you all about it. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, Robotics, IoT and other fun tech. Remember to subscribe and join the community. I've used these high wonder servos on a few of my projects and I've used some of their kits too. You may remember the X-arm, which I adapted to be driven through ROS2 and drove through a Raspberry Pi Pico 2. I was using the High Wonders driver boards though to control the servos, and I still needed a level shifter to interface to the Pico 2. I like modules. They accelerate my development and give me tried and tested features. This does though come at a bit of a cost. Each of those modules is going to need lots more additional connectors to my Pico, and those connectors, often DuPont connectors, are not very reliable, at least for me. So my projects are like my RexPi droid turn into hedgehogs. In this video I'm going to explore interfacing to that High Wonder LX-16A servo and see how few components I can use to actually drive it from a Raspberry Pi Pico. I'll ask the question about stability and reliability too. If you like this video and it helps your learning on projects, then why not drop me a cash tip using that super thanks button below the video, or there's a payment link in the description. Remember, I'm saving these up to get myself to the open source conference in San Francisco. That's a long way from here in the UK and a lot of expense too. I'd appreciate your help in getting me there, and I'd love to meet you all there too. Please hit the like button on the video and subscribe for more.
This video is sponsored by PCBWay. Every robot engineer needs a good partner to help with building PCBs and robot components. PCBWay is that perfect partner. PCBWay strive to be the most professional PCB manufacturer for prototyping and low volume production work in the world, which makes them a go-to place for makers like me to help me fabricate and assemble my low volume PCBs in their own in-house production service. PCBWay have lots of options for PCB types and coatings, along with instant quotations through their website for most services. They can help with project hardware too, through 3D printing, CNC machining, sheet metal work, or injection molding. Get some inspiration from the community on their project site, or buy some ready-made modules from the module store. Go take another look at PCBWay.
This video is all about bus servos, and in particular the Lewan's Soul or High Wonder bus servos. And the one I'm going to work on is the LX-16A. Now, bus servos typically need an adapter board to drive them. That's because they actually have a particular serial protocol rather than just responding to a PWM signal. So on the connector that goes out to these servos, we've got both the ground and the voltage that we might see on any servo, but then a control signal, and that control signal is actually serial communication. So that's a bit different from, say, an MG995 standard servo, where that still has a control signal, but the control signal is there a PWM signal that is allowing us to set the angle. Here on these bus servos, we're actually sending it a command, and that command might actually be to rotate to a particular destination, but also at a particular speed. It also could be to actually go into continuous rotating mode, or to read back data too. So I might read back what is the temperature of that servo, what voltage it's actually getting, and what its current position is, which is really useful for us in robotics. The other really useful thing is these servos can be chained. So instead of everything having to go back to the microcontroller, we can actually just connect one servo to the next servo to the next servo, and as long as we can get enough power through that chain, we can actually control a whole set of servos in one go and just use that single pin, single couple of pin connections into our microcontroller. Now, I've used these bus servos before on a number of projects, but I've always used them with a controller board. And controller boards are great, but they do mean that I've then got a lot of connector wires running around and more than I'd really like. After all, one of my reasons for using servos, bus servos, is that I can actually chain them and reduce the number of connections I've got. So can I actually drive this LX-16A directly from my Pico, or with just some standard electronics in between that I can actually then build onto my own controller board that will have my whole RP2040 controller based on the board? Well, let's have a look at the spec and what's involved in this. Now, the advice from Highwonder is that if you want to connect these up, you should be implementing a circuit that looks something like this. They recommend these 74126 buffer connections that allow us to basically connect the transmit or receive lines to the single comms UART line going into the robot, or disconnect them. And that's what they're doing there. They're basically tri-state connections, which is possible on those. So we can also see that the signal here is 5 volts. So our Pico is definitely 3 volts. So we're going to need some line control or level shifting involved. And we also will have to think about how we're going to do TX and RX buffered communication. So how do we actually disconnect, transmit and receive, so that we end up with a protocol that's in effect half duplex, so only one side is communicating at a time. So we've got our Pico and we've got 2 connections coming out of our Pico for transmit and receive, and I'm using those off of GPIO 20 and 21. Now, I can put a diode on there just so that my receive and transmit, or my transmit pin, which is GP20, isn't actually getting any data coming back into it, which would be bad. So I could put a signal diode on between the two. In this configuration, I can even actually transmit out of one pin and read the data back via the next pin, which is kind of weird, but it does work, and that is a useful way, and that's something I was playing with. So that gives us UART communication potentially coming off of our Pico. Now next, I'm going to need to put that into some sort of level shifter, because I need to get that up to 5 volts. Now, of course, these bidirectional level shifters are ideal for that, because I've actually got the values going in both directions, so across there. So we can definitely use that, and use that to drive then a connection going out towards the robot. Now, the spec does also say that the output going into the robot needs to be pulled up by a 10k resistor to 5 volts. So I can do that as well, and that gets us to the connection going out to our servo, and that should all work. I'm going to put 6 volts across the other 2 connections so that we got enough current and power to actually drive the servo, and I'll put a capacitor there just to make sure that we, not getting any browned outs or issues. But I think that should be enough to actually connect directly our Pico to the servo. But I'm going to have to do some stuff in software. So my software for this is going to be an experiment that I've placed here within my AstroDroid projects repo. And it really is an experiment. It probably should become a library at some point, but right now it's an experiment. But it does show the concepts of what we need to do. There are 2 problems that I'm trying to actually address in this. I need to worry about electrical buffering. So how am I avoiding transmitting and hearing everything back on the receive pin, and making sure that these are isolated and that there is no electrical connection as we're running between transmit mode and receive mode in our half duplex communication. And then of course the comms protocol itself, which takes some work too, because we've actually got to send out a whole message structure with a checksum in it and receive that back. So first of all, this electrical buffering, well, that's really disconnecting transmit and receive when they're not in use. Now, in every serial communication example you've ever written with a Pico, you've added these two lines or a version of them into your code that says set the function for this pin to be UART function, and you set it for the transmit pin and you set it for the receive pin. And in effect, what that's doing is connecting that pin through to the UART function, peripheral function within the Pico's architecture. Now, there is another function there that you could have actually set it to called null. And it's my assumption and a statement that I think that is the same as basically disconnecting that pin and putting it into a tri-state mode. So it's a mode where it's basically not connected. So I think we can actually use that to actually switch in and out when we have transmit and receive connected and operating. So if in a write function, therefore, we first of all connect up our transmit pin to the UART function, then do our write, then we can actually disconnect it and we're all good. And I can do the same with read. Now, there is a little bit more than that that we'll have to worry about, and I'll show that when we go through the code. But in principle, I think this is enough. Though on the read side, there is also another bit of complexity. We really need read with timeout, because if something goes wrong and we're just sitting there waiting for data, then our whole application is going to collapse. So we will have to implement a read with timeout capability just to make sure that we handle things when comms goes wrong. How about the protocol? Well, the protocol that these things send is basically a header of 2 bytes of value hex 55, followed by the ID number of the server that you want to change, the length of the data, which is just from the ID number up until the end of the parameters, the command code itself, the parameter you want to send as part of that command, and finally a checksum, which we need to calculate and put in there. And we will get exactly the same fallback back from the servo if we're doing a read response, read request. So that's what we need to write. Let's have a look at some code. So this really is an experiment project that I've set up here called LX-16A, and it's within my Astro Droid project. It's providing standard out over UART, which I'm going to use for telemetry to see what's going on, and I've redirected standard out to be over pins 16 and 17, as I tend to do, just for clarity on that. And then I'm going to use the second UART on it as well, and the second UART, which is UART1, is what we're going to use to connect to our servos. So that's on GPIO 20 and 21. So the code for this really is fairly simple. What I'm just going to do is basically set up that UART1 so that it's at 115/200 baud, however you pronounce that easily. And then I'm basically going to go through a loop, and I'm going to go through a set of commands which I'm just going to move 2 servos. Let's move servo 1 there to position 50 in 500 milliseconds, move servo 2 to position 200 in 800 milliseconds. Then I'm going to actually use the this function here to get back the voltage that is currently being read by servo 1, get the voltage for servo 2, get the voltage limits that that's set to for servo 1, print that, and then move some servos again. So I'm just testing out some functions and some capability. So really, I suppose we should talk about how are we going to write and start. Well, let's start with a simple command. How are we going to move a servo? So the move servo command, it's actually 10 bytes in length, and it looks at has a structure where it's basically the two start bits, 0x55s. It's got a checksum at the end, and then the data is going to be in the middle. And the data starts by us actually saying, well, which servo number is, and that came in from the function. It's command 7 to move. Then it's the length of the function is 7. That's and so we're going to actually have 7 bytes through the middle here. Then the function number is function number 1. And then I need to do a little bit of maths to prepare my angle that I want to. So what I'm actually doing is setting an angle on this, and I need to compute the angle and set that to into 2 bytes. So we got the high byte, which is going to be in byte 6 of our command, and byte 5 is going to be index 5 is going to be the low byte. So I'm just really cutting them out. Each degree is actually 0.24 degrees, or 0.24 as calculated by the number that the servo knows and it's going to return. So that's how I do it. It's fairly simple there. And time, that's even easier because we don't need to convert that. It starts in milliseconds. We just need to chop it. So we're putting the low byte into index 7 and the high byte into index 8. And then we've got checksum. I'll talk about checksum in a second. And that will give us the bytes. And I'm doing a little bit of debug here and just printing that out as well. And then we can write that to the UART. And that should go and tell our servos to move. So we've got a couple of little functions in here I should talk about a bit more then. So first of all, checksum. The checksum on these servos is basically just the sum of the data values and then negated. And so I've just got a little loop here that's going to go through all of those values and then negate it. So that's easy enough. The read and write are perhaps the more interesting bit. Write's very easy actually, because the first thing I'm going to do now is I'm going to actually connect up our GPIO pin for transmit. So I'm going to use the GPIO set function that we talked about earlier, and then I can use a blocking write function to write out all of the data. Now I know that only writes it and blocks until it is in the FIFO ready to go out of the UART. Actually, because the next thing I'm going to do is turn off that pin, I need to wait for that FIFO to actually clear. And to do that, I use the UART-TX wait block command, and that will wait until that FIFO is clear. Once that FIFO is clear, then I can actually disable that pin. So that's our buffering approach. We're connecting using the set function and disconnecting using the set function again. So that's how write works. So we now know enough to be able to actually move and do most things with a servo. It's only when we actually want to read data back that it's something slightly different. So we're doing that in a function like getVin. This is a smaller function. It's actually only has the length of 3 values in the middle there. I've actually put a lot more I know in that command buffer, but that was copy and pasting. And it's command 27. So basically it's got 2 start bits followed by the servo number, the length, which is 3, command 27, and the checksum. We've seen how to do a checksum. We've seen how the write works as well. So that's all good. Now the next thing we're going to do is we're going to read back the result of that. And the result is going to be fairly similar in structure. So we will still see 2 start bits, a servo, a number of length and command, and then some parameters and a checksum. So I know in the buffer that I've got from my read, provided my read was successful, that actually the millivolts that it's being read for this servo and it can read is has the low byte in position 5 or index 5 and the high byte in index 6. So I'm just going to OR those two together, and that should give me the nice millivolts value. So how's read working? Because read, you might notice, has got 3 parameters on there. The buffer to read to, the length of the buffer that we're expecting, and we've got a timeout. That's 500 milliseconds timeout there. So read is, of course, first going to, first it's going to set up some timeout data. So it's going to calculate what time we should time out. And it's going to calculate the value now so that we can keep reading until now is greater than timeout. Then we're going to set our read pin to actually be enabled, so it will be a UART function. And then we can go and keep checking to see if we've actually got any data available. If we have, then we can read it and we can keep building up our data. Now I've put a little bit of filtering in here to make sure that when we start reading, the first thing we should expect in the first byte should be a start bit, i.e. 0x55. In fact, we should get 2 0x55s. I'm just not checking that. I could do a lot more checking here than I am, but I'm just doing some simple to try and get us to where is the start, then to read the data. Once we, so the end conditions on this are, if we get the index gets to the length that we're expecting, then we've got all of the data. We can turn off our read pin and we can back out of here. The other potential is that we time out and we run out of time to actually read the data, in which case we again turn off the read pin and we return out, and this time we'll return a false. So that's what I'm using in order to read back data, and I can do that the same process for any of the write or read commands. So I think it's demo time. So without a control board in there, so just using the connections through our level shifter and this connect capability, we're actually driving these 2 servos. They're connected serially and they are reliably turning exactly as they're meant to. One is taking slightly longer to turn than the other, but that's what I told it to. So yeah, all good. And I've also got some telemetry, so I can see from here I'm reading back some data around the voltage being available to each of the servos and the volts limiting values on servo 1, and I'm getting those all back correctly, which is great as well. So in my test, the comms seems really quite resilient and it all seems to actually work quite well. I think I have a result here. My approach in this video does move away from the recommendations of Hiwonder in their design guide. I'm not using the recommended buffering chip, but the RP2040 and indeed RP2350 have their own buffering capability, I think. That's how we switch features onto the different GPIO pads. So I think my approach is sound. Yes, I have also got this to work without a level shifter driving the commands and just using 3.3 volts. The replies from the servo is at 5 volts though, and although to an extent an RP2040 is 5 volt tolerant, I'm stressing it here. So for long-term stability operation, I should use a level shifter. I can drive these servos directly from a RP2040 or an RP2350 board though, without that annoying driver board. So moving away from my hedgehog approach to a significantly reduction in the number of connectors I need, which is really cool. This is a massive result for me. If you like this video and it helps your learning or projects, then why not drop me a cash tip using that super thanks button below the video, or there's a payment link in the description too. Remember, I'm saving these up to get myself to the open source conference in San Francisco. That's a long way from here in the UK, and I'd appreciate your help in getting me there and I'd love to meet you all there too. Thank you very much for watching. Please do like the video and please subscribe so you don't miss the next video. And I'll see you very soon. Bye bye.